We're now going to take a look at higher order derivatives. Let's start by considering a simple function like y equals x to the fourth. Now this is a differentiable function, so we could find its derivative and it would just be y prime of x equals 4x cubed, just by the power rule. Now this derivative is itself just another function of x, so there's nothing wrong with taking the derivative of it. So we're going to take the derivative of the derivative. When we do that, we get what we call the second derivative, and we would denote that by y double prime of x. And in this case, that would just be 4 times 3 x squared, or just 12x squared. So this is what we call the second derivative. Now this is just another function, so there's nothing to stop us from taking the derivative of it. And we would get what we call the third derivative. That would be the derivative of the derivative of the derivative, is what we're doing. And we would denote that by y triple prime, like this, of x. And in this case, that's going to be, well, we drop the 2 down. The 12 is just a constant. It just hangs around, doesn't do anything. Drop the 2 down, you're going to get 24x. And we can keep doing this. We could then take the fourth derivative. Now, we don't use prime notations for the fourth derivative. Beyond 3, we usually use notation like this. We'll put a 4 there, and we'll put it in parentheses so that this distinguishes it from meaning y to the fourth power. When you see a number in parentheses like that, it normally means the fourth derivative, or the nth derivative, whatever number is in here. Now in this case, this would just be 24, derivative of 24x. Remember, the derivative of x is just 1, so 24 times 1. And we could take the fifth derivative. Now the fifth derivative from here on out, the fifth derivative of y is just going to be 0. And from there on out, all of our derivatives are going to be 0 for this particular function. So these are what we call higher order derivatives, and there's a very good reason why we would want to consider them, as we'll see in a few minutes. Now here's some notation for derivatives. We use the prime and double prime and triple prime notation up here, but there's other notation down here we have indicated. The first derivative, well, we've already seen how that's indicated. We can use y prime or f prime or dy dx or df dx. And sometimes you'll see this notation, although we don't use that very often. The second derivative, you have the double prime notation here and here, f double prime. Now you also see this notation. Notice we have this d squared dx squared of y, or d squared dx squared of f. Notice the location of the 2's, how the top 2 is with the d and the bottom in the denominator, that 2 is with the dx. The reason we have the 2's located there is because when we take the second derivative, we're thinking of taking the derivative of our derivative function, of our derivative of y, derivative of our derivative. So you see right here would be our first derivative, that's just y prime, and then this indicates right here that we're taking the derivative of the derivative. Now notice how these d's are side by side. So in the top we were thinking of 2d, so that's like a d squared. And in the denominator we have the dx's side by side, so we think of dx squared. And then the function y is just sitting to the right of those. So that's why we put the 2's in these locations to indicate the second derivative. You do not put them aside of the y, or in the exponent of the y. And then we have similar notation for the third derivatives. Notice d cubed dx cubed of y, or d cubed dx cubed of f, and this notation as well. And then for the fourth derivative, we stop using the primes and we use this type of exponent notation here. And we can still use the d4 dx to the fourth notation as well, and so on. All right, so those are what we call higher order derivatives. We're just taking derivatives of derivatives. Let's look at an example. So here we're given the function f of x equals x squared sine x, and we want to find the second derivative. Well, we first need to find the first derivative before we can find the second derivative. So the first derivative of this function. Now, we're going to have to use the product rule here, right? Because it's x squared times sine x. So we're going to have to go x squared times the derivative of the sine. So that's going to be x squared times the cosine of x, plus, then we have to go sine of x times the derivative of x squared. So that's going to be 2x times the sine of x. Okay, so that's our first derivative. Now we just have to take the derivative of this function, and that'll give us our second derivative. So f double prime. Now, we have to use the product rule on this piece and on this piece, and then just add them together. So for the first term here, the product rule is going to yield x squared times the derivative of cosine. The derivative of cosine is negative sine, so I'm going to put a negative right there, sine x. Plus, then we have to go cosine times the derivative of x squared. All right, now that is the derivative of the first part. Then plus the derivative of this, and we'll have to use the product rule again. So it's going to be 2x times the derivative of sine, plus the sine times the derivative of 2x. And the derivative of 2x, remember, that's just going to be 2, because the derivative of x is 1. And there we go. That's our second derivative. We can clean that up a little bit, combine some terms. We can write this as, let's see, we have 2x cosine plus 2x cosine. That's going to be 4x cosine of x. Plus, and then we could combine the two signs, factor out the sign from this term, and we'll get 2 minus x squared times the sine of x. And that is our second derivative. Let's take a look at another example. So here we're given the function 1 over x, and we want to evaluate the first, second, third, fourth derivatives, and then make a conjecture about what would the nth derivative equal. All right, so, well, let's write down our function. That's just 1 over x. And let's notice that that is x to the negative 1. That'll help us to differentiate it. Now our first derivative, by writing it as x to the negative 1, we don't have to use the quotient rule here, right? Makes it a little easier to differentiate. So the derivative of this is going to be negative x to the negative 2. We drop the negative 1 down, subtract 1 from up here, and we get this. And let's write that as negative 1 over x squared. Now let's take the second derivative. So let's differentiate this. So we're going to drop the negative 2 down. Now negative times negative 2, that's going to make it positive 2, x to the negative 3. And we'll write that as 2 divided by x cubed. Now let's take the third derivative. So we'll use this form to differentiate. So we drop the negative 3 down. 2 times negative 3 is going to give me negative 6. In fact, let's leave it like this. I'm going to leave it as negative 2 times 3 x to the negative 4th power. It'll help us to identify what f to the n is going to be. Of course this is 6, but let's just leave it like this for now. And so this is going to be negative 2 times 3 divided by x to the fourth. Then the fourth derivative, now we're going to drop the negative 4 down, so it'll be 2 times 3 times negative 4, and this negative will cancel with this negative. And then that'll be times x to the negative fifth. And we'll write that as 2 times 3 times 4 over x to the fifth. Now, of course, we could write this as 24 over x to the fifth, but we just want to leave it like this so we can recognize what f, the nth derivative of f, is going to be. Now, notice that this one up here, the first function, that's when n was 0. All right, I'll put a little 0 right here. That was a 0 derivative, the original function. This was our first derivative, second, third, and fourth. Now notice a pattern here. Notice we have in the exponent here in the denominator we have a 2 and our n was 1. That was our first derivative. Down here our exponent is 3 and we had a 2. Here our exponent is 4 and we have a 3. Here our exponent is 5 and we have a 4. So we would conjecture that the nth derivative of f is going to be, well, it looks like it's going to be, we're going to have an x to the n plus 1 in the denominator. Okay, you see, we can see that from the pattern. Now you notice we have a 1 here and a 1 here, a 2 and a 2, now that's actually 2 times 1, a 3 and a 2 times 3, a 4 and a 2 times 3 times 4. The next one would be 5, and we would have up here 2 times 3 times 4 times 5, and you see the pattern, minus, plus, minus, plus. This would be a minus here, x to the sixth. Now we call this a factorial. You see, this is 1 times 2 times 3 times 4 times 5. That's called, this is the same as 5 factorial. And this, the numerator here would be 4 factorial. 1 times 2 times 3 times 4. That's 4 factorial. There's a 1 out here, we just don't have it written there. So we're going to have up here then n factorial. Really, that's 1 times 2 times 3 times 4 all the way out to times n. Now we have this minus that's occurring. It's changing. Minus, plus, minus, plus, minus. So we're going to put a negative 1. And if we put that to the nth power, that will give us the pattern that we need. Notice when I take the first derivative, n is 1. So negative 1 to the 1 power, that'll give me this negative right here. Now here we don't have a negative, and if we put 2 in for the n up here, negative 1 squared is positive, and so we don't get any negative right here. When n is 3, we want a negative here. Well, notice negative 1 to the third power, that is going to be negative. And then we don't want any negative here. Well, when n is 4, negative 1 to the fourth, that's going to be positive. And so this is our nth derivative right here. The nth derivative would be negative 1 to the n times n factorial divided by x to the n plus 1 power. That's what this pattern is indicating here. This one, this one, this one, this one, and then this one down here. All right. Now, let's take a look at this. Let's take a look at some applications of higher order derivatives. So, if you remember, when we were talking about throwing an object upward or downward near the surface of the Earth, remember that we had a position function given by something that looked like this. And so we called s of t our position function. Now remember, when we found the velocity then by taking the derivative of our position function. Now if we take the derivative of the velocity, that's going to give us what we call our acceleration. So the acceleration is your change in velocity. And so a of t is dv dt, or v prime. Notice also that that's actually the second derivative of your position function. So the acceleration of an object is the second derivative of your position function. Let's take a look at an example here. So if an object is dropped from a height of 500 feet, first of all, let's find the position function of the object. Well, for part A, our initial velocity, since it's being dropped, our initial velocity is 0, and our initial position is 500. So our position function is then going to be that's simply our position function, negative 16t squared plus 500. For part B, let's find the velocity and acceleration of the object. So the velocity is going to be the first derivative of our position function. And the derivative of this is just going to be, remember the derivative of a constant is 0, so we just get negative 32t, dropping the 2 down. And our acceleration is then the derivative of our velocity function. And when we differentiate this negative 32t with respect to t, that's just going to give us negative 32. Now the units here, the units of the position function were in feet. The units of our velocity are feet per second. And the units of the acceleration would be in feet per second, or feet per second squared. Notice that we just recover negative 32. That's just the acceleration of an object in free fall near the surface of the Earth. So we just recovered that negative 32 for this particular problem. And that makes sense. If you drop an object near the surface of the Earth in free fall without any other forces acting on it, its acceleration is going to be negative 32. Then finally for part C, find the velocity when it strikes the ground. Alright, so for part C, well, we need to find how long it takes until it strikes the ground. So we need to set the position function equal to 0 and solve for t. So when we do that, we get, and then solving this for t, this implies that, so I'm going to take the negative 16t squared over, put it with the 0, divide the 16 under the 500, and we're going to get t is 500 over 16. And then we have to take the square root of that because of the t squared right here. And then that's going to be approximately 5.59 seconds. Now this is how long it takes the object to strike the ground, 5.59 seconds. If we want to find the velocity of the object when it strikes the ground, we have to take this number and put it into our velocity equation right here. We need to put that number in for t. And what we get then is v of 5.59 is equal to negative 32 times 5.59. And that comes out to be negative 178.88 feet per second. And so that is the velocity of the object when it strikes the ground, negative 178.88 feet per second. Notice it's negative because it's falling towards the ground, which is the starting point for our measuring system. Now let's take a look at another example. Now in this example, we have a top fuel dragster, accelerates from 0 kilometers per hour to 525 kilometers per hour in 4 seconds. We want to find the acceleration of the dragster, assuming that the acceleration during the dragster's run is approximately constant. So during that 4 seconds, the acceleration of the dragster is approximately constant. That's what we're going to assume. Now, just to put this into some perspective, if you're used to the imperial or English system, 525 kilometers per hour is approximately 326 miles per hour. So a top fuel dragster, meaning that it's burning nitrous oxide, actually can accelerate from 0 to 326 miles per hour in about 4 seconds. They really can do that. It's amazing how powerful they are. And the distance that they travel during that time is about 1/4 of a mile. So, all right, well, let's find the acceleration of this dragster. Now, we're going to use units of meters per second. You know, near the surface of the Earth, we usually measure acceleration in meters per second. Like near the surface of the Earth, acceleration due to gravity is negative 9.81 meters per second squared. So let's put everything into common units of meters per second. Notice we have 4 seconds here, hours over here, and kilometers. So we're going to turn everything into meters per second. Well, notice that 525 kilometers per hour is, if we replace the kilometer with 1,000 meters and the hours with 3,600 seconds, that's how many seconds are in an hour, and we simplify this fraction here, we get 145.83 meters per second. So 525 kilometers per hour and 145.83 meters per second, those represent the same velocity, just different unit systems. Okay, so, well, acceleration then, recall, your average acceleration actually, is your change in velocity over your change in time. Now our change in velocity, the dragster starts out at 0 meters per second. 0 kilometers per hour is the same as 0 meters per second. And after 4 seconds is traveling 145.83 meters per second. So the difference between those is, of course, 145.83 divided by 4 seconds, and you get 36.458 meters per second squared. So that's the acceleration, assuming that it's constant, during that 4-second run. Notice that the units are meters per second squared because the numerator here, that's velocity, has units of meters per second, and the denominator has units of seconds. So when you simplify this fraction, you get meters per second squared. And there you go. That's the acceleration experienced by that dragster. Now, just to put that into perspective, gravitational acceleration is negative 9.81. So if we take this number and divide it by 9.81, that is approximately 3.72, and what that represents is we usually call that unit G's, the number of G's that the driver would be experiencing in that car, in that dragster, as it's accelerating. To put that in perspective, you may have heard, if you know anything about aviation, that fighter pilots in fighter aircraft can experience anywhere from 7 to 9 G's of acceleration before they black out. So 3.72, that's pretty many G's for a dragster driver to experience. Also considering that during that 4-second run, your acceleration isn't usually constant. At first, they might be experiencing 5 G's of acceleration, and then that would decrease in the latter half of their run. Okay, and then that concludes this discussion about higher order derivatives and their applications.